Hello everyone, and welcome to this video on section 7.1 called Parametric Equations. In this video, I'm going to be taking you through a preview version of a Newton-Alta assignment for this section 7.1. Please understand that in this video, the questions I see may not be the exact same questions that you see when you work on the assignment yourself, but the objectives are the same. Hopefully the problems are similar enough that watching me do them here will help you when you work on the assignment on your own. Okay, so here's our Newton-Alta page. You have the title of the assignment in the upper left-hand corner. You will not see the word preview. You have the mastery bar in the upper right-hand corner, telling you how far along you've gotten. Next to that, an activity log, showing you how far along you've gotten in each individual objective. So it looks like for this assignment, there's one big objective, one big heading with 3 sub-objectives. Back on the main page, you have your current objective. Underneath the current objective is a question related to it. And at the bottom of every question, you should be seeing a feedback button. So if there are any issues with the question itself, or maybe the answer explanations when you see the answers to a question, you can send feedback directly to Newton, and hopefully someone from their support team will get back to you quickly and resolve your issue. You will not have this instructor cheat button, right? This is for instructors only. You will have a more instruction button though. All right, if you're struggling with a topic or a particular question, click on this more instruction and you'll be taken to another page with further reading to do or videos to watch or both. And then you'll be given questions that are related to that instruction. And you can work on those questions while the instruction is still up, so you can keep referring back to it for help. And you can work through the entire assignment this way. Every time more instruction comes up, you can click on it, work through a problem, and keep making progress in the assignment. All right. So the first objective here, write parametric equations. So parametric equations in 2 dimensions anyway. We're only going to be working in 2 dimensions with x coordinates and y coordinates, right, on the xy plane. We have a curve that's called a parametric curve if both x and y depend on another variable or variables, but for the most part, we're going to be dealing with x and y depending on one variable. And I'm seeing that they're calling that variable t. Now, if both coordinates, your x coordinate, your y coordinate, depend on t, they're going to call t a parameter, and the equations parametric equations. And the curve would be a parametric curve. So in this question here, we're asked to determine a pair of equations that can parameterize, right? That's just a fancy word for, hey, have x depend on t and y depend on t. Parameterize the curve x to the 4th equals negative 8x plus 5y plus 9, all right, using x of t equals t as one of the equations. All right, so I'll write that up. So they're telling us that the x coordinate of any location we're at is just the value of our parameter t. And here's the rectangular version of the equation, right? When we're in rectangular coordinates, that's just x and y, right? X coordinate, y coordinate. So the rectangular version of our curve, the equation in rectangular coordinates for our curve is this: x to the fourth equals, negative 8x plus 5y plus 9. Okay, and I'll show you what this looks like on Desmos real quick. You can actually, the nice thing about Desmos is, you can type in an equation as it looks. It doesn't have to be solved for y or anything. So x to the fourth, equals negative 8x plus 5y plus 9. And here's this curve, right? And then on the line below it, I'll show you how to graph in Desmos parametric curves where you have the x-coordinate and y-coordinate of some curve depending on some other variable, some parameter called t. All right, anyway, back to this. So they're telling us what to use for x. Have x depend on t this way. So the value of x, the x-coordinate of any location I am at, is simply going to be the value I choose for the parameter called t. Well, if I substitute this into the rectangular version of the equation, every x is replaced with t. We have, t to the fourth equals negative 8t plus 5y plus 9. And then you see now it becomes an equation with y and t. And I can solve this for y, to get the y of t, right? To get y in terms of t, what is the y coordinate of the location I'm at value t? So I'm taking this here after substituting x equals t and solving for y. Now to solve for y, I would add 8t, subtract 9, and then divide everything by 5, right? Hopefully you can do the algebra there. So y would be equal to, t to the fourth plus 8t minus 9, and then all divided by 5. And there's your y of t right here, describing where you're at for different values of t. All right, let me again go back to Desmos and show you how to enter parametric curves, parametric equations. In Desmos, you have to enter them as ordered pairs. So like you put parentheses and then the x-coordinate is just the value of your parameter t, and then comma, and then how does the y-coordinate depend on t, right? Maybe type in all this. T to the fourth plus 8t minus 9, 9, all divided by 5. Right, close the parentheses. You kind of enter it as ordered pairs. So I'll show you. And we're going to see the curve that comes up could match. Well, it's going to give a range of values for t. And I'll show you what's going on here. But let's put parentheses. The x-coordinate, depending on t, was just t. Then comma. And then the y-coordinate depends on t this way, t to the fourth plus 8t minus 9, and then all divided by 5, close parentheses. Now you see initially, it just has the values of t ranging from 0 to 1. So you see that just gives me this little piece of the red, it's part of the red curve, clearly, right? Just from when t equals 0, right? So that'd be this point down here, 0, negative 9/5, right? When t equals 0, the x-coordinate would be 0, and the y-coordinate would be, negative 9/5. That's this point here. And then when t equals 1, you'd be at the point 1 and then 1, 0, right here. So you see when I look at the graph, just the blue graph, right? It's starting when t equals 0, right? Starts when t equals 0 and ends when t equals 1, and just that piece of the curve. So if I wanted to get more of this red curve, I would just change, now you could just say have t be all real numbers, but on the Desmos calculator, I can't put in like infinity, right? If I try infinity here, let's see what happens. Negative infinity to infinity, I don't think anything's going to come up. Yeah, so nothing really happens there. See, they're like, hey, invalid domain, right? Try using an actual number. So I can't just put in all real numbers. Now, if it was all real numbers for t, we'd get the entire curve. Let's say I just go -5 for t. So remember, that's just also the x coordinate. So we're going to see from -5 up to, I'm just going to go to 2 here so we can actually see. Maybe I'll go -3 to 2 just so we can see it without having to zoom out. So from -3 for t to 2 for t, and you see we're getting this blue curve here. All right, again, it's the same shape. It's exactly on top of the red curve. Right, but just from when t equals -3 up to when t equals 2. Right? But that's parametric equations. You describe your location, your x coordinate, your y coordinate in terms of a third variable, right, called a parameter. In this case, it's t. Right, well, back here, we got our y of t. It was 1/5. I'm just putting 1/5 instead of divided by 5 times the quantity, t to the 4th plus 8t minus 9, right? And then close the parentheses there. Okay. That should be what they wanted. Submit. Great. And they actually divided every term by 5 here, but it's the same thing. As long as it's equivalent, they'll take it, right? And then after you submit an answer, right, you'll be given some sort of answer explanation. Please look through these, right? If you were correct, glance through them to make sure you got it right for the right reasons, that you didn't just guess correctly. And also, maybe they do something in the answer explanations that you like better and would like to try for future problems that are similar. Now, of course, if you got the question wrong, read through the answer explanations, right? That way, hopefully you can figure out while reading where you went wrong and can learn from your mistakes for future questions that are similar. Okay. All right, so now we're to graph parametric equations. So like I was showing you here, right, when you graph a parametric equation, unless they say t can be all real numbers, right, they're not asking for the full graph. They're just going to be asking for part of a graph, right? Like here when t was, from the last example, I got my parametric equations here, and I'm only ranging the value of the parameter from -3 to 2, and I get this partial graph here. So yeah, you see how they have this range of t. Now they're making a little table for us. All they're asking us to do is fill in a table down here with inputs and outputs, right, with x coordinates and y coordinates. So see, fill in the table of values that can be used to sketch the curve described by the parametric equations. X of t equals 7 times the cosine of 5t, and y of t, right, the y coordinate depends on t this way, sine of 5t, where t ranges simply from 0 to 2 pi over 5. All right, so I'll make this table here. Now there's obviously other values we could plot. All right, but let's take a look. All right, we got our parametric equations are the following. X of t, the x coordinate for any given value of t, is 7, right, times the cosine of 5t. Right? And then y of t is just the sine of 5t. All right. So I'm going to do this. All right. You don't have to I mean, the title of the objective is graphing, so I should be able to make a rough sketch myself. So you make tables just like you would when you're graphing any other function, any other curve, right? This isn't necessarily these are two functions, but we're going to see that when we graph it, we're not going to have y as a function of x. Anyway, but just like, you got these three variables now, right? You got your inputs are all t, right? This value of the parameter t. So I'm gonna make a table. And then for each value of t, there's your x coordinate. So x of t. And then also the corresponding y coordinate, right? Y of t. Now they're putting in, they're also having t range from 0 to 2 pi over 5. Now when t equals 0, right, at the low end here, plug those in. X of 0 would be 7 times the cosine of 0. Now the cosine of 0 was 1, so this would be 7. All right, so I'll do this here on x coordinate of 7. Let's say there's 7. And a y coordinate of, the sine of 0, which was 0. All right. So the point that this curve, when I'm drawing it, the point that this will start at is the point 7, 0. Right. And I'll put next to this point here. This is the point I'm at, where t equals 0. That's where I'm located when you could almost think of the parameter t as time. At time 0, I am here. And then we'll see what happens as time goes on, as the value of t changes. Of course, you can have negative time sometimes, though, so that wouldn't make a lot of sense, maybe going back in time, but whatever. Okay, and then the next value they have in the table on the assignment, or in the homework problem, is pi over 6. Pi over 6 for t. Now, when I plug in pi over 6 here, you get 7 times the cosine of 5 pi over 6. So remember the cosine of, I'm not going back to the unit circle or trig or anything. I'm not re-explaining any of that stuff. Just the cosine of 5 pi over 6. That'd be the negative square root of 3 over 2, and then times 7. So negative 7 times, square root of 3 over 2. Now square root of 3 over 2 is about 0.86. So say about 0.8, and then times 7, you get about negative 5 point something. So here's negative 5, here's negative 6, so maybe negative 0.86 times 7, somewhere between, somewhere around here, between negative 5, negative 6, negative 7. And I could go to a calculator and find it, but I'm not doing that just yet. And then the sine of 5 pi over 6, right? T is pi over 6. The sine of 5 pi over 6 was a half. So 1/2. So x coordinate somewhere over here, y coordinate a half. And I'm just going to kind of eyeball this. Go there. So there's where when t equals, pi over 6, I'm at this location. Right. And actually, we're going to see this moving this way. From this point to this point. We'll connect the dots in a little second here. And then they plug in pi over 3. Right? Pi over 3. And when I plug in pi over 3, uh, the x coordinate would be 7 times the cosine of 5 pi over 3. Now the cosine of 5 pi over 3 would be positive half. So we're at positive 7 halves or 3 1/2 for the x coordinate. 3, 4, there's There's 7/2, and then the y-coordinate would be the sine of 5 pi over 3, which would be negative square root of 3 over 2, right? About negative 0.86, but less than -1. Here's negative square root of 3 over 2 or whatever. And this isn't a very good drawing, but 7/2 for the x-coordinate, negative square root of 3 over 2 for the y-coordinate. And here's when t is pi over 3. Right? And we could plot more and more points of this by plugging in different values of t from, ranging from 0 to 2 pi over 5. Now, honestly, because both of these sine and cosine have, 5t in it, that's one period of sine and cosine here. And I would honestly, if I were doing this myself, I'd break that period into quarters, right, and plug in every pi over 10. All right, so let me do that. So I start at 0. So again, these are our answers. They want us to fill in this value, this value, this value, and this value in the homework problem. But if I was actually making the graph myself, I'd take a period of these trig functions, 2 pi over 5, cut it into quarters. That'd be every pi over 10, and then plug in pi over 10. Now, 7 times the cos, 5 pi over 10 is pi over 2. That'd be 0. And then the sine of 5 pi over 10, sine of pi over 2 is 1. All right. So 0, 1. That's when p equals pi over 10, which is coming before pi over 6. So the curve is going to be doing this. And then the next pi over 10, so 2 pi over 10, I'll plug in pi over 5. All right. Cosine of pi was -1, so that's at -7 for the x-coordinate, and sine of pi was 0, so -7, 0. So I'm over here at -7, 0, when t equals pi over 5, right, 2 pi over 10. And then when t equals 3 pi over 10, this would be cosine of 3 pi over 2, 15 pi over 10, which is 0, so I'm back to 0 for the x-coordinate. And the sine of 3 pi over 2 is -1, so I'm at 0, -1. And I'm here when t equals 3 pi over 10. And then when I'm at 2 pi over 5, we're back to the initial point, right? We'd be back at 7, 0. So at 0 and 2 pi over 5, I'm back here. And if you were to plot more and more points, look at the way this is going here. The graph is doing this as time and as the value of the parameter increases. And usually they put little arrows on things, the orientation tell you which way something's going. So as t increases, we're going around in this like oval shape. All right, it's actually going to be an ellipse. We'll talk about eliminating the parameter later. You know how in the previous example I had the rectangular equation, with just x and y and no t. We'll talk about doing that later. If I give you parametric equations, can you write the equation for the curve without t, with just x and y? We'll see later an equation like this, or parametric equations like this, actually determine an ellipse. And I'll show you in the Desmos too. I go to Desmos. Let me put in those. Make sure I'm in radian mode, by the way. Yeah, radians, okay. So again, ordered pair here, parentheses. Now the x-coordinate was 7 times the cosine of 5t, and comma, and then the y-coordinate was the sine of 5t. And look at that, you're seeing part of this oval shape and it's like I drew by hand, right? But we're having t range from 0 to 2 pi over 5, right? And you see the entire ellipse here. t equals 4, but okay. Yeah, you see the entire ellipse. I just want to see if you can make a table. Doesn't look like you can make a table here. All right. Okay. So back in the assignment, right, it's filling in when t was 0, the x coordinate was 7, the y coordinate was 0. When t was pi over 6, the x coordinate was -7 times the square root of 3 over 2. And when t was pi over 6, the x coordinate was that. And when t was pi over 3, the y coordinate was a negative square root of 3 over 2. And that's all they want us to fill in here, not actually make the graph. Okay, great. And again, hopefully they show you the graph. They do not. Yeah, so the graph would again be this ellipse, or like you saw, it's again like the thing I had in the paper here. I plugged in a lot of other points, sure, just to see it forming. But you should be able to do that with any of these parametric equations. Hopefully you plug in enough values of t to where you see a pattern forming, then you can kind of figure out where the graph is going. And it's like that with any graph, right? When you first were introduced to graphs with just x and y, right? That's how you made graphs. You plugged in different values of x, different values of y, found different ordered pairs, and hopefully you found enough to where you saw a pattern forming and then filled in the rest of it. Okay. All right, so here's the eliminate the parameter in parametric equations. So this is where you're asked to write the parametric equations below as a Cartesian equation. So Cartesian means rectangular. I had the word rectangular up in the first problem of this video. Cartesian means rectangular, xy. Write it as an equation with just x and y in it and no parameter. Now this time the parameter is not called t, it's called theta, right? As long as x and y depend on some third variable, some other variables, they're called parametric equations, and those other variables are called parameters, okay? So, I mean, I could replace theta with t here, and it would still be mean the same thing. Okay. So here are the parametric equations we are given. And it's just like the last example where one of them involves a cosine, the other one involves a sine. So the x depends on this parameter called theta this time, right? Again, you can call it t if you want. And it's equal to -9 times the sine of 2 theta. Again, you can call that 2t if you wish. And then y depends on this same parameter theta, and it's equal to -9 times the cosine of 2 theta. All right, now I'll give you a little tip here. Usually when we're trying to eliminate, when they say eliminate the parameter, and that means, right, what they called in the problem there a Cartesian, or what I called in the first problem, the first example here, a rectangular, sorry, that's an N, rectangular equation, right? That's just involving x and y, no parameter, no theta, no t, right? So usually you're going to substitute, you solve for the parameter in one equation and then substitute for that parameter in the other equation. All right, so we may come across ones where we'll want to do that, but I'll give you a tip right now. These parametric equations that involve sine and cosine of the same argument like this, sine of 2 theta, cosine 2 theta, you're going to be making use of this. Recall that cosine squared of something. So again, I'll just use x, maybe not x, a. How about a? Because there's already theta up here. Plus, and then sine squared of that same argument, will always be equal to 1. So these parametric equations here that involve sine and cosine, I'm going to use this fact. So what we do is we solve for the trig functions. Solve for sine and cosine, solve for cosine, solve for sine. Now in the first equation, and this is just, I'll call this just x. This is the sine of 2 theta is equal to, negative x over 9. And then same thing with this y of theta, I'm just going to call that y. And if I get the cosine alone, we have the cosine of 2 theta is equal to, negative y over 9. And by this, what we know from trig, if I were to square both of these and add them up, I'd get 1. Right? So, the cosine squared, negative y over 9 squared plus the sine of this argument squared, negative x over 9 squared should be equal to 1. And this is our, Cartesian equation now. See how there's no more theta, no more parameter, just x and y. Now, of course, if I square this stuff, this is y squared over 81 plus, and then this is x squared over 81 equals 1. So this is the equation of an ellipse, but where the major axis and minor axis are the same, so it's actually a circle. All right, I can multiply everything here by 81, and I'm going to put the x squared first. We have x squared plus y squared must be equal to 81, a circle. Right, it's a circle with a radius of 9 centered at the origin. And we can see that, right? Watch, right? We can see that when we go to our parametrics. Now in the parametrics, when you're doing parametrics in Desmos, right, you kind of got to enter t instead of theta here. All right. So my x coordinate was negative 9 times the sine of, now it was 2 theta in the problem, but I'm going to say 2t here. And then the y coordinate was negative 9 times the cosine of 2, again, 2t. And because these are trigs, I'm going to go from 0 to, now the period for sine of 2t and cosine of 2t would just be pi. I can just go 0 to pi for t to get the whole circle. When you see this circle with a radius of 9, right, so that's 9, not everything 9 units away from the origin. Circle, radius of 9, center of the origin. X squared plus y squared, I'll type that in too. X squared plus y squared, all right, equals 81. And you see it's exactly the same graph. But with no more parameter, there's no more t, no more theta, it's just x and y, right? Just a Cartesian. And that's what I'm going to be typing in. You see here x, I'll do x squared plus, and then the next box, y squared equals, and then the next box, 81, and submit that. Great. Now they have x squared over 81 plus y squared over 81 equals 1 like I had earlier, but they're the same equation. All right. So that's how you would eliminate parameters when sine and cosine are involved. Again, we might see some other problems where you just have to make a substitution from one equation into the other to replace the parameter. So back here, back to graphing these parametric equations. All right, so determine which graph is the sketch of the curve described by the parametric equations. So we see x of t is cosine 3t, y of t is 7 sine of 3t, where t ranges from 0 to 2 pi over 3. Now you can make a table and do a graph by hand here, but I'm just going to go to Desmos. Now this should be an ellipse again. This is going to be another ellipse. You could do elimination of the parameter and see that x squared plus, y over 7 squared, so y squared over 49 equals 1. And that would be an ellipse with a center at the origin, vertices at 0, 7, 0, -7. So, and then co-vertices at 1, 0, -1, 0. Okay, but look at the arrows on it though. So remember I said a lot of times on these parametric curves, they'll put an arrow on it to tell you which way things are going. All right, so perhaps I should plot just a couple points. So it's going to be the second or third one. All right. No, I'll just go to the Desmos. We'll put those in just to make things a little quicker here. You could again plot things by hand and see how things are going. But the first coordinate, right? The x coordinate was cosine of 3t, comma, and then the y coordinate was 7 sine of 3t. Now, you see when t equals 0, or if I just go t equals 0 here, the first point we're at is here, 1, 0. Or that should be 1, 0. When t equals 0, cosine of 0 is 1, sine of 0 is 0. So we're starting here, and then if I go t equals 0 to, say, 1, well, they want 0 to 2 pi over 3, and I'll let this play very slowly to see how the points are moving. I'll have the step be, say, every 0.01 or something. So when I play this, see how the point is moving in a counterclockwise direction. I'll go up to 0, 7, all right? So we'd be tracing out this curve, and I'll draw the curve out in a second, the full curve. But you see that if I keep increasing the value of t, we're going along this ellipse in a counterclockwise direction. I'll label it, see what the coordinates are. But so I'm gonna get rid of this and then go back up here and just have this be what they wanted, to actually graph the dots, 2 pi over 3. Oh, pi. I forgot the pi. There. And you see this ellipse. Again, they started here at 1, 0, and as t increased, we're going counterclockwise around this ellipse. All right, so back here, this second option is going clockwise. See the arrow going down here. So it's not that one, it's this one, where it's this ellipse, but the arrow's, pointing me in the counterclockwise direction. As t increased, I was moving around this counterclockwise, so that's the graph. All right, great. So back to writing parametric equations. So we write x in terms of t and y in terms of t here. And this time they don't give us x of t. They want us to find equations for both. So here a particle moves in a straight line from point A, -9, -7, to point B, -6, 5, in 15 days at a constant rate. The coordinates are given in meters with respect to the standard xy coordinate plane. Find the parametric equation with respect to time t. So the parameters t is time, representing time in days, for the motion of this particle. So it's going from point A to point B. I'll write this information out. So on the xy plane here, so we're moving from point A, which is at -9, -7. All right, so here's -9, -7. All right, that's the point A they were talking about. And moving to point B, which is at -6, all right, so to the right there, -6, 5. There's point B. And the motion is, it says it's a straight line motion. So from here to here in that direction, right? Little arrows on there. So what we would like, now t represents time in days, right? T is equal to the number of days that have passed. And they said that this motion occurs in 15 days. So t is going to range here from 0 to 15. So I would like this to happen. Here, I want when t equals 0, I want to be here at the point -9, -7. And then I would also like, when t equals 15 to be at the point -6, -5, right? Now, being that this is a straight line stuff, moving at a constant rate, it should be pretty simple. Notice how x of t here, well, when t is 0, the x coordinate's 9 less than that. Same thing for at 15, right? When t is 9 less than that, 9 less than 15 is 6. So I'm going to guess here that x of t is just t minus 9. Right? That'll give me the x coordinate. And then what I'm going to do next is, again, this is the point -9, -7. This is the point -6, 5. I'm going to write the Cartesian equation, right? The rectangular equation for this. Right, rectangular / Cartesian equation. Now the slope of this line, right, the slope of this line, remember, is, change in y over change in x. So it's 12 for the change in y, right? Went up 12 over 3. So it has a slope of 4. And then I'll just use one of these points. I'll just use this point down here, y, to write the equation in point slope form, y minus -7, so y plus 7, equals the slope times the change in x plus 9. There's the rectangular equation for the line that this segment's on. And then I'm going to take what we know x to be, right? The x coordinate is always 9 less than the t value, right? And I pop that in here, right? We're going to substitute that for x and then solve for y here. So y plus 7 could be 4 times, and then if x is t minus 9, t minus 9 plus 9 would just be t. And then subtracting 7, y is going to be 4t minus 7. All right, so y of t is, 4t minus 7. And here we go. Right? These are the parametric equations we're asked to find. And you see when t equals 0, you'd be at the point -9, -7. And when t equals 15, 15 minus 9 is, ooh, no. That's not correct. 15 minus 9 is +6, not, okay, not -6. All right, so I have to do something different here. My apologies. I'm sorry about that. I just made a silly arithmetic error. 15 minus 9 is not -6, +6. I am sorry. I am sorry. All right, so let me redraw this. My sincerest apologies. I will leave a comment or a note in the description of the video mentioning that error. So again, we got, so same picture, my bad. All right. So x, y, starting at -9, -7. So here is point A, -9, -7, and it moves to point B at -6, +5. Right, maybe I made it too easy last time, right? It was too simple. There's point B, and this was the motion, right? It was a straight line motion from A to B, right? And we want it so that when t equals 0, right, we're here, and when t equals 15, we're there, right? And now at a constant rate, right? They mention the words at a constant rate. Now remember, constant rates of change. If the rate of change is constant, we're talking linear, right? Linear functions here for our values of x and y, right? So x of t and y of t must be linear, right? So for x, x needs to be equal to, say, mt plus b, right? So I'll call it m1t plus b1, right? A linear function. So we want, again, we want tx, right? When I plug in a value of t and get x, when I plug in 0 for t, I get -9 for x. Also, when I plug in 15 for t, I want -6 for x. So the slope of this linear function relating x and t, and I'm calling it m1, it'd be the change in output, all right, the change in output. So -9 minus -6, -9 plus 6, so -3, and then divided by, and then 0 minus 15, -15. So +1/5, right? And then, the intercept here when t is 0 is -9. So we have 1/5, x of t is 1/5 t, and then -9. Right, so you see that'll work out, not just t minus 9 like I had. So you see 1/5 t, when I plug in 0 for t, that would give me -9, like I want. And now, right, when I plug in 15, 1/5 of 15 is 3, and 3 minus 9 is -6. So this is much better. This actually gives me the correct value of x at t equals 0 and t equals 15. And then I'll do the same thing I did in the previous page, where I do the Cartesian. So again, not everything was bad on the previous page, just my x junk, right? Now the Cartesian equation, I had this up right on the bad page, but that was this here, in point slope form. Now the slope of the line containing this segment is 4, and it does contain the point, -9, -7. So we got y plus 7, equals 4 times x plus 9. And then I'll pop in our parametric equation for x to get a parametric equation for y. So y plus 7 would be 4 times, and then x is replaced by a 1/5 t minus 9. Now a 1/5 t minus 9 plus 9 would just be 1/5 t. And then we subtract 7 here, and we got y equals, 4/5 t minus 7. There we go, 4/5 t minus 7. I could have also done the same thing that I did with x. Things are moving at constant rates. So y should be, say, m2 times t plus b2, right? Some linear function of t. And we know that when we plug in a value of t, we're going to get a value of y. And the following points are on it. When t equals 0, y equals -7. So that would be like the intercept. That'll be b2, right? -7 we're seeing here, right? So 4/5 t minus 7. And then another point, was 15. And when t equals 15, y equals 5. And when I find m2, right, the slope here, that'd be -12. for the change in output divided by negative 15 for the change in input, and that's positive 4/5. And so I'm getting the same equation here, 4/5 t minus 7. So there we go. That's a lot better. So again, my apologies for the earlier page and the bad arithmetic I did. The 15 minus 9 is negative 6. That's not correct. All right. So yeah, so here's what I'm going to enter. And just to double check, let's go to Desmos, and I'll put in these parametric equations here, right, in parentheses as an ordered pair. The first one was t divided by 5, 1/5 t minus 9 for the x's. And then the second one was 4t over 5, 4/5 t minus 7. And then we're going to have t range from 0 to 15. And look, see, you get that part of a line. And you see, I'll plot the points that they started off at point -9, -7. That should be at the bottom of this. All right, see, it's right here. Starting at -9, -7 when t equals 0. And then this point at the end of this segment should be the point -6, 5. And look at that, right? Now they don't give they don't write arrows on this. But I could do the thing where we see the point moving again. All right, so I have, maybe t equals 0 and then put in a t equals 0 range to 15. And I'll have it go by, say, 0.01, and we'll play it real slow. And what you're going to see when I start playing this is that we're starting here at the point -9, -7, and as time t goes on, it'll move along a line to this point -6, 5, right? So you see the point moving as t increases, and we're moving in a straight line motion at a constant rate of speed, until we get to the point -6, 5, when t equals 15. And I'll let it play out, right? It's not going to take that much longer. 11, 12, 13, 14, and then you see it's coming up here at 15, stop, at -6, 5. Great, so those are correct parametric equations. So again, we had t divided by 5, 1/5 t minus 9 for the x coordinate, and then 4/5 t minus 7 for the y coordinate. Wonderful. Again, they explain all that, and they're doing the same, talking about how, hey, when there's constant rates of change, that means you're on a linear functions. Great. All right. All right, so now we're asked to eliminate the parameter again. So remember, this is where you're given parametric equations and asked to write the Cartesian equation that matches that curve. So get rid of the parameter here. It's t again. All right. So rewrite an equation with x and y. Now they have down here y equals. So I want to write y equals and then some expression with just x, no t. So this is one where you can make a substitution. Right? There's no sines or cosines here like in previous problems. So we have x, again, I'm just going to call this x, but x of t, x equals -4t minus 1. And then y of t, or just, y, is -10t minus 9. So to eliminate the parameter, then you just kind of, when trig functions aren't involved, the trig functions, you can use a nice, nice identity to get rid of those parameters. But here I have some nice linear functions. So we solve one equation for the parameter and substitute into the other. So if I solve the first equation here for the parameter, that would be x plus 1 divided by -4. All right, so t equals x plus 1, and then divided by -4. And then you substitute into the other equation. Sub into other equation. And there you go. Then you'll have an equation where parameter is eliminated. There's no more t. You just have a Cartesian or rectangular equation with just x and y. So now you have y equals, -10, and then t is, x plus 1 divided by -4. And then, -9 after. Now, of course, I'm going to simplify this, -10 over -4, that's positive 5 halves when you reduce it, times, they got this quantity x plus 1 minus 9. And this should be good, but I'm going to put it in slope-intercept form. Y equals 5 halves x, and then plus 5 halves minus 18 halves, that'd be minus 13 halves. All right, 5 halves times 1 is 5 halves. Times 2 over 2, this is 18 halves. Again, 5 minus, hopefully I'm not subtracting incorrectly like I did in the previous problem. 5 halves minus 18 halves would be negative 13 halves, and here you go. All right. And once again, we can kind of test this out with Desmos. Let's go here, get rid of all this stuff from the last problem. So if I put in my parametric equations, the x coordinate was -4t minus 1, comma, y coordinate -10p minus 9. Now you see here when t equals 0, you'd be at the point -1, -9. So that's starting down here. So here's part of the line. Right, t equals 0, you're starting up here, and then it's going down to this point here when t equals 1. So that's just a part of the line. Now let's put in the line we got after eliminating the parameter, right? Y equals 5 halves x, and then minus 13 halves. And see that that's right on top of that green segment there. All right, that's right on top of it. So those parametric equations and this Cartesian equation are actually describing the same curve. So yeah, y equals 5 halves x minus 13 halves. That's what I got after eliminating the parameter, making that substitution. Great. All right. All right, so we're back to graphing. What's this? All right, so use Desmos to graph the curve represented by the parametric equation x equals -4 secant t, y equals negative cosine t on the interval from 0 to pi over 2. It says move the blue point to the correct location for t equals 0 by clicking and dragging it. So the blue point when t equals 0. The arrow should indicate the direction traced by the graph as t increases. It can be changed by clicking and dragging the blue point on the slider in the upper left-hand corner. So you see if I move this here, it'll change the arrow. This is going that way. Now it's going the other way. All right, well, if x is -4 secant t, remember secant 0 is just 1. So we start at -4 and then -1, right? Cosine 0 is also 1. So we'd be starting at the point -4, -1. All right, so I'm going to move this blue point here when t equals 0 to -4, -1. That's that point there. And then as t increases, from 0 to pi over 2, I would imagine it would go outward from there. So I'm going to change this to this, right? Because like when t equals pi over 2, well, remember secant of pi over 2 is undefined. So going to infinity, actually, as you approach pi over 2 from the left, secant of pi over 2 would get toward large infinity. So this is So the x coordinate's going to negative infinity, which I'm seeing here. So definitely going that way, the arrow. The x coordinate's going to negative infinity as t approaches pi over 2. And then the y coordinate, as you approach pi over 2 from the left, the cosine is approaching 0. But from the negative side, because you got this minus in front. So you see I'm approaching x coordinate negative infinity, and the y coordinate c is approaching 0 from below. So it's definitely this arrow. Now, I could go to Desmos, like they said, and put these in and make sure I'm in a radian mode here. And you see negative, what was it, -4 secant t, comma, and then negative cosine t. All right, yeah, and you can see that, and I'll do the little when t equals 0 thing. We'll see how the point moves around. T equals 0, put a little start at 0. Let's just go out to what they wanted here, pi over 2, and then go steps. Let's just do 0.01 again, and I'll play this really slowly so we can see how the points are moving. All right, so see, it's starting at the point -4, -1, like I said, when t equals 0, and then you see it's definitely moving very, very slowly, but to the left. See, it's moving to the left. Yeah. Now, if I were to eliminate the parameter, we can actually see it moving on the curve. Um, you know, remember secant is just a reciprocal of cosine, and secants are just reciprocals. So like if x is -4 secant t, that would mean that x is equal to -4 over cosine t, which is the opposite of y. So it's just x equals 4 over y, all right? But we can restrict things to where, x is just less than or equal to -4. All right, so that's where we started at negative, when x was -4 like this. So if I go back again, right, you can see the point. You can see our point here moving. I'm actually going to change this to 0.1 instead of 0.01, so it moves a little faster. Play this, and you can see this black point, moving along this curve this way, toward the left, like the arrow was. I don't see it slowly moving. But then the closer you get to pi over 2, it starts shooting out real quick. Right? Oh yeah. Okay. So yeah, so this is our correct graph here. Great. All right. Okay. So these curves, these functions, hyperbolic sine and hyperbolic cosine. If you go back to the section 6.3/6.4 videos I've made, there's, I think, 4 of them, one for each objective. I introduced you to these hyperbolic trigonometric functions. So I'll refresh you here. So they're asking us if, determine the type of basic curve set of parametric equations represents. Is it a parabola, circle, an ellipse, a line, hyperbola? Now, it said the word hyperbolic. These are called the hyperbolic sine, hyperbolic cosine. That's why the H is on the end of them. This is going to be a hyperbola. All right, and I'll show you. Let me put these in. Back here, we got, zoom this out a bit. So we had our x coordinate, right, was given as 9 times the hyperbolic sine of 9t, 9 times and then sin h of 9t, comma, and then 9 hyperbolic cosine of 9t, right? So the y coordinate 9 hyperbolic, cosine, cosh of 9t. And then you'll see if I make t larger and larger here, we go, let's say, from -10 to 10. See how it's part of, you can't see the other branch though. We're getting part of a hyperbola. You'll see here that it's y squared. I'll write up the identities in a second. Y squared over 81 minus x squared over 81 equals 1. All right, and see how it's that green curve up there is just the top part of this hyperbola. So this is a hyperbola. All right, and I'll submit it, but let me go to some paper and I'll refresh you as to what these hyperbolic sine and cosine do. All right, some identities involved with them. So again, this hyperbolic sine, S-I-N-H of something. So again, I'll do I don't want to use X, Y, or T. So again, I'll just do like capital A again here for argument. So the hyperbolic sine of something is defined this way. It's defined as half of e to that value, then minus half of e to the opposite of that value. And then hyperbolic cosine is defined using exponentials as well, e to powers. It's defined very similarly, but with a plus. It's half e to the a, half of e to the argument, plus half of e to the opposite of that argument. Right? So you can define these, and again, I brought these up, I introduced these in the section 6.3/6.4 videos. And then a property of these is that the hyperbolic cosine of some argument squared minus the hyperbolic sine of that same argument squared will always be equal to 1. So it's like for trig, it was cosine squared plus sine squared equals 1. For these hyperbolic trigonometric functions, it's hyperbolic cosine squared or cosh squared minus hyperbolic sine squared sinh squared equals 1. And so when we have, x equals, 9 times the hyperbolic sine of 9t, and we have y equals 9 times the hyperbolic cosine of 9t, just like I did with the regular cosine and regular sine, the circular functions, solve for the hyperbolic sine, hyperbolic cosine. The hyperbolic sine of 9t would be x over 9, and the hyperbolic cosine of 9t would be y over 9, and then I'm just putting these in here and here to give me y squared over 81 minus x squared over 81 equals 1. And remember, this is the standard form equation for a hyperbola. You might have to go back to maybe pre-calc 1 or some college algebra class the last time you saw one of the equations of these maybe. But that was a hyperbola with a center at the origin, vertices at 0, 9 and 0, -9, asymptotes y equals x and y equals -x, and and all that. Right? Yeah, so definitely a hyperbola here. Right? And they take you through it. Right? So again, it's just the top half of it, the top branch. Back to more graphing, parametric equations. All right, so this is another multiple choice deal. Right, where notice the little arrows on the graphs too, right? Some of these look the same, but the arrows are going in different directions. All right, so determine which graph is the sketch of the curve described by these parametric functions where t is, negative 8.5 to negative 3.5. Now notice that the x equals, t plus 6, and y is just negative 3 over t plus 6. So y, if you were to eliminate the parameter, y is negative 3 over x. All right, so I'm going to put these in the parametric equations with this, and then also the y equals negative 3 over x. So our x coordinate was, t plus 6, come on, t plus 6, comma. And then the y coordinate was negative 3 over, t plus 6. And the value of t ranged from negative 8.5 to 3.5. So we're on this curve here. Maybe I'll change that to a different color. There's red, okay. Or whatever color you're seeing. All right, so you see it's, now when t is negative 8.5, we'd start at the point where x is negative 2.5, so that would be this point on the far left here. And as t increases, the x coordinate's going to go up, so we're going left to right. We'd have to be going left to right on this curve. So we're going to see this curve here with arrows going from left to right on it. So of the pictures that we're seeing, I know I said I was going to graph y equals negative 3 over x, but I don't feel like it right now. So of the pictures we're seeing, this is the same graph, but you see the arrows are right to left. It's this bottom one, right? It's the graph we were looking at, but the arrows are going left to right. So this is the curve that we would get if we were to graph those parametric equations. Great. Now they do a whole table thing here. This is very similar, but all they're doing now is asking us to fill in a table. So we saw one like this earlier. So I'm just going to say these things out loud. So fill in the table of values that can be used to sketch the curve. So if x is t minus 9, so whatever the t value is, the parameter value, x is 9 less than that. So down here, 21 halves minus 18 halves would be 3 halves. So 3 halves for that x. 11 minus 9 is 2. And then 23 halves minus 9, again, 18 halves, that'd be 5 halves. So notice all these x things here, just kind of going up by a half every time. All right, now the y value is just negative 10 divided by the x. All right, you see the x is t minus 9. Y is negative 10 over t minus 9. So whatever the x coordinate is, I'm just doing negative 10 divided by that. So take the reciprocal of the x coordinate times negative 10. All right, so here, reciprocal of the x coordinate is 2 times negative 10 would be negative 20. Here, the reciprocal of the x coordinate is 1 times negative 10 would be negative 10. Here, the reciprocal of the x coordinate is 2/3 times negative 10 would be negative 20/3. And then that's it. They only want us to fill in that table. Great. All right, so that graph parametric equations sub-objective is done. All right, now we're asked to go back and, we're in this eliminate the parameter deal again. All right. All right, so here you can solve for t if you want, but here's something I'm noticing here, that they both have this negative 7t involved. So again, we got x of t is negative 7t, negative 7t plus 7. And then y of t is negative 7t plus 9. Now again, like we did earlier, you can solve for t in one equation and substitute to the other one. Oh, I got to read the instructions. So look at this. Determine the domain that results from eliminating the parameter in the set of parametric equations below. So what's the domain? So after I eliminate the parameter, they want the domain of the function that results. All right, so that's still going to be eliminating the parameter here. Now again, you can solve for t in one equation, substitute for t in the other, and then you'll get just an equation in x and y, right? A rectangular equation or Cartesian equation. But here's something I'm noticing. They both have this negative 7t plus something. Now, negative 7t plus 9 is actually the same thing as negative 7t plus 7 and then plus 2. And negative 7t plus 7 is x. So we're getting y equals x plus 2. Now, this is a linear function. All right, the graph would be just, like this, y equals x plus 2. Slope of 1, y-intercept of 2. The domain is all real numbers here. The domain, after eliminating the parameter, we're getting the equation of a curve that I can plug in any value of x for. So the domain of this function, resulting after eliminating the parameter is all real numbers. Now in interval notation, that would be from negative, infinity to infinity with parentheses on either end. All right, so negative infinity, comma, infinity. And that's all they want. So yeah, you see that. Now they actually solve for t, substitute, right? They get y equals x plus 2. And there's the graph of y equals x plus 2, clearly has a domain of all real numbers. Great. All right, so this one's different. They're not asking for the domain, but they are asking us to eliminate the parameter. All right, so write the parametric equations below as a Cartesian equation. So again, take these x of t, y of t, and they want, now notice here they have y equals. So I want y equals and then just something with x, right? No t. Okay. So back here, and you can do this a couple ways. And one of them is just solve for t in the x equation, right? We have x is e to the 9t minus 8. If I solve this for t, you'd have e to the 9t equals x plus 8. And we do natural log of both sides and then divide by 9, right? So natural log of x plus 8 plus 8. And then divided by 9 gives me the value of t, right? So t equals, 1/9 times the natural log of x plus 8. So there's solving for the parameter in the x equation. And then y was e to the negative 10t and then plus 9 after. And I'm going to make this substitution, right? Replace t with 1/9 the natural log of x plus 8. Well, that's giving me this, y equals e to the negative 10/9 times the natural log of x plus 8 and then plus 9. Now this is totally fine. If you type this in, they should give it to you. But I'm going to simplify this a little bit more. I'm going to take this number here, put it in as a power, right? Use that power property for logarithms. And so now I have y equals e to the, just the natural log of something, the natural log of x plus 8 to the negative 10/9 power, and then plus 9. And then e to the natural log of something, those undo each other, inverses. So y equals just x plus 8 to the negative 10/9 power and then plus 9. And this is a little less cluttered to me, so I'm going to type that in. And you can double check, graph the parametric equations for values of t, graph this, and see that they match. See that the graph of our Cartesian equation goes right over the graph of our parametrics. So yeah, I'll do that. All right. So I've done this before, right? So our parametric equations, x equals e to the 9t power minus 8, comma, y coordinate was e to the negative 10t power, and then plus 9. All right, so you see the curve there, starting with t equals 0 to t equals 1. Now if I graph that's just from t equals 0 to t equals 1. Now if I graph what I got from the Cartesian, y equals x plus 8, raised to the negative 10 ninths, and then plus 9. You see how that overlap, the red graph is being overlapped here, right? It's part of that curve. So our Cartesian equation matches the curve that's described by the parametric equations, right? So y equals x plus 8 raised to the negative 10 ninths power, and then after that, plus 9. This should be good here. Wonderful. Now they wrote it with the 1 over x plus 8 to the positive 10 ninths, right? Just the reciprocal of the negative power, but it's still the same thing. All right. Another eliminate the parameter, but this time, right? Determine the domain that results from eliminating the parameter in the set of parametric equations below. All right, so this one's not as nice as the last one that we had with this, because they're not both linear. Uh, yeah, okay, so I'm gonna eliminate the parameter, and we'll state the domain of the resulting equation, right? The values that you can plug in for x, right? All right, so here are the parametric equations. We have x. It's getting kind of faint, sorry. So we got x equals 6t plus 3. So that would mean that t is 1/6 of the quantity x minus 3, or x minus 3 all divided by 6, whatever. And then y is the square root of t, sorry, 7 times the square root of t plus 3. And I make this substitution for t. So y equals 7 times the square root of 1/6 times x minus 3, and then plus 3 after. Now, the square root of 1/6 is a constant, so I'd have 7 over the square root of 6, square root of 1 over square root of 6, and then times the square root of x minus 3, and then plus 3. Now, when we're talking domain here, remember square roots, even roots, the expression inside has to be non-negative, right? X minus 3 has to be greater than or equal to 0. So x must be greater than or equal to 3, telling me that the domain of this function is, 3 or greater, right? Numbers 3 or greater when I put it into interval notation here. And we can make the graph of this, look at the graph of this, and you'll see the graph of it is only from 3 to the right. No values less than 3. Right? So interval notation, 3 and onward, bracket, 3, comma, and then infinity, and then parentheses. Great. So again, they take you through it here, blah, blah, blah. Same deal. There's the graph of our Cartesian curve, right? When we eliminated the parameter, this y equals 7 times the square root of x minus 3 over 6 plus 3. That's the graph of this here. And you see how it's only graphed from 3 onward. Right, great. All right, so there's one last little objective left, the sub-objective, write parametric equations. Okay, so let me see if I can redeem myself here. This is a very similar problem to what we saw that I made the little error, the little boo-boo earlier. So it's moving from one point to another point on a straight line in so many hours of time at a constant rate. Again, when they say something's moving at a constant rate, that tells you linear functions are involved, right? Linear equations. All right, and then find the parametric equations with respect to time in hours for the motion of the particle. So I'll draw a similar picture to like the problem similar to like the one we had with this before. So here's the XY plane, and we're moving from the point 3, -2, right? So 3, -2 is the initial point. So this is what they were calling point A, and this is when t equals 0, right? I want to be there when t equals 0. And the final point is at -5, -5, right? So -5, -5. This is the point they were calling B, and I want to be there when t equals 55, right? They said t was time in hours, and that this straight line motion took 55 hours. Straight line motion at a constant rate took 55 hours. All right, so we want the following, right? So x is going to be some linear, again, if we're moving at a constant rate, both x and y are going to be some linear function. So like I did earlier, say x equals m1 times t plus b1, right? If I want to put it in slope-intercept form. Now, we're looking at ordered pairs like this, input t, output x. I want when t is 0, the x coordinate to be 3, and I also want, when t is 55, I want the x coordinate to be -5. All right. So 3 is going to be my b1, right? That's the intercept, right, when t is 0. So b1 is going to be 3, and then m1, right, the slope of this thing is, 3 minus -5, which is +8, over, and then 0 minus 55, -55, -8 55ths. So x of t is going to be -8 55ths times t, and then plus 3. And we can double check, when t equals 0, x is 3. So we're starting where x is 3. And when t equals 55, you'd have 55 is canceling. -8 plus 3 is -5. I'm over here. So there's the x coordinate in terms of t. And then same thing for y. Y is going to be, say, I'll put it in slope-intercept form here, m2 times t plus b2. And we want, when I find points on this, when I find pairs that satisfy this, we want when t equals 0, the y coordinate to be -2. So that's going to be my b2, -2. And we would like also when t equals 55, the y coordinate to be -5. Right? And then from these two, I can find the slope, right? m2, the slope of this linear equation describing the y coordinate. -2, minus -5 would be +3/2 divided by -55, so -3 55ths, right? So the y of t, the y coordinate at any given time, is -3 55ths times t, minus 2. So there's the x, there's the y, and double check, when t equals 0, you're at a y coordinate of -2, that's the y coordinate of a. And when t equals 55, the 55s would cancel, you'd be at -5 for y. So these work out for this linear motion at a constant rate. So, yeah, so x of t is, is -8 55ths t plus 3. And y of t, -3 55ths t minus 2. And those should work out. Right. Alrighty. All right, so here's determine a pair of equations that can parameterize the curve. So it's like the very first example from this video where they give us a parametric equation for the x coordinate. They tell us how x depends on t as t plus 6. And then here's the Cartesian equation or the rectangular equation. Then I just need to solve for y, get y in terms of t. So very, very similar to the first example from this video, hour and a half ago. So the rectangular equation is this, -2x squared equals 5y minus 6. And they give us this, x of t is t plus 6. So that's x. That's just replacing x in this equation. And then I can solve for y. So I have -2 times the quantity, t plus 6 squared equals 5y minus 6, and then I can add 6 divided by 5. So I'm going to do this. Y equals, -2 times the quantity t plus 6 squared, and then plus 6, all divided by 5. And seriously, I'm just going to enter this. They should give it to me. It's equivalent to what they want. So in the numerator here, -2 times the quantity t plus 6 squared plus 6, and then all of that in the numerator divided by 5. That should be good. Great. Yeah, they actually wrote it a different way, but it's equivalent. And it looks like that's the last of them. All right, so there we go. That's it for this preview. And like I said at the top of the video, the questions I saw here may not be exactly the same as the ones that you see when you work on it yourself, but hopefully they're similar enough that watching me do them here helps you out in some way, when you go to work on it yourself. And thank you very much for watching.